For example, let me use a 1D Poisson's equation as an example. In this case, A is equal to 1 over delta x squared times minus 2, 1, 1, 1, 1. All right? That's what the matrix looks like in a 1D Poisson's equation. And of course, D is equal to minus 2 identity over delta x squared. That's the diagonal part of this matrix. It's just the minus 2 over delta x's. Okay, L plus U is equal to 1 over delta x. I'm just basically making the diagonal zeros, otherwise are the same, right? And you ask the question, why don't I combine L and U? Here I'll combine L and U. So the Jacobi iteration is saying I want my U at I is equal to D inverse times B minus L times, L times UI minus 1 plus U times UI minus 1. Here is basically, L plus U. I mean, I should be minus. If I put a parenthesis here, it'll be L plus U. If I don't, it's L minus U. Okay, now I'm going to expand this into index format. So what is this L plus U times UI minus 1 at a particular index K? So basically, if I take the kth row of this matrix times a vector, what is it? Yes? Yes, so first of all, it only has access to the neighboring nodes because this row only has non-zero entries at k minus 1 and k plus 1, right? Okay, so, and the coefficient on the entries are exactly 1 over delta x squared. So this is UI minus 1 k minus 1 plus UI minus 1 k plus 1 over delta x squared, right? And then once we know this, we can write down what is the UI of k. It is equal to, first of all, the D inverse is just the 1 over the diagonal entries of D, which is minus 2 times, I'm just going to write, let me write it down so that it's clearer. dkk, and dkk is equal to minus 2 over delta x squared, right? Okay, times bk minus this guy, delta x squared, UI minus 1 k plus 1 plus UI minus 1 k plus 1. All right. So this, now you can see why I'm doing this. I'm starting to get away from the matrix. Now I start to see I don't really need to have the matrix in the memory. I have converted a matrix operation just into a what we call a stencil operation. An operation that is an algebraic operation, a linear combination of like neighboring values. Yes, thank you. It should be minus 1. Thank you. All right. Okay. Then I plug in this dkk. What I get is, first of all, the coefficient on B is just 1 over dkk. It's minus delta x squared over 2 times bk. And all of these becomes plus. So it's plus half of uk minus 1 I minus 1 uk plus 1 I minus 1. All right, that's what the Jacobi iteration looks like. It is taking a linear combination of the right-hand side at the same grid point and the last iteration value at neighboring grid points. All right, I'm going to do the same thing for the 2D Poisson's equation. So please make sure you understand how it works in 1D. Any questions? No? No? Okay. 2D Poisson's equation. I'm going to do this a little bit faster. My matrix A is equal to, so let me do a special case where delta x is equal to delta y. Okay, so that makes the notation a little bit simpler. My A is going to be equal to, again, 1 over delta x squared. Now what is the diagonal? What is the diagonal? -4, because I have contribution from the x direction second order derivative and y direction second order derivative. Okay, and I have 1s here breaked by zeros during the blocks. I have 1 here break by zeros, and I also have some 1s here, 1s here. Does everybody remember what it looks like? Okay. My D diagonal is equal to -4 over delta x squared times identity. That identity is a big identity. It equal to, it's basically the size of the whole mesh, whole grid. And L plus U is equal to 1 over delta x squared. The diagonal becomes 0 and everything else is the same. All right. Okay, now let's go to the Jacobi iteration method. My U at I is equal to D inverse times B minus L plus U times U of I minus 1. So everything is the same except for D inverse, which is 4 instead of 2, and also L plus U. So let's figure out what is L plus U times U I minus 1 at a particular grid point. Maybe I shouldn't use I here. Let me switch. Sorry for the notation, but let me use K here for the iteration, and because I need I and J for the grid point. All right. Okay, it's a switch of notation. Please make sure it's clear, like the difference between 1D and 2D. In 1D, we use the K as the grid point, I as the iteration number. Here, we are switching K to be the iteration number, and I and J is reserved for the X direction index and Y direction index. Okay, this at I and J is equal to what? If I multiply this matrix, and I look at a particular row of the matrix corresponding to the row I of the grid and the column J of the grid. So this is in the I direction, this is the J direction. We are looking at a grid like this. What is this matrix vector multiplication at grid point I and J? What are the non-zero entries? The 4 neighbors, yes. Very good point. The 4 neighbors. So the non-zero entries involve 1 over here, 1 over here, 1 over here, and okay, so I put it in the first block. That's unfortunate, but like if it's, let's say if I put it over here, it's 1 here, 1 here, 1 here, and 1 here. So basically it has 4 non-zero entries. All have the same coefficient, 1 over delta x squared. And they correspond to the neighbor upward, the neighbor downward, the neighbor to the right, and the neighbor to the left. So if I write it down, it is equal to 1 over delta x squared times u k minus 1 I minus 1j, u k minus 1 I plus 1j, u k minus 1 I j plus 1, u k minus 1 I j plus 1. Right? And now we can write down uk, I, and j. It is equal to 1 over dkk, which is this thing. I'm just going to directly write it down. It's delta x squared over 4 and the minus sign times b at I and j minus this guy. Any questions? And that again is a stencil operation, right? It involves the linear combination of the right-hand side at the very grid point, and also linear combination of the previous iteration value at the surrounding, the neighboring grid points. Yes. So what happens if one of the diagonal entries is 0? Then don't use Jacobi iteration. Very good point. Jacobi iteration requires your diagonal to be full rank so that you can invert it. All right, if your diagonal entry is 0, then don't use Jacobi iteration. Any other questions? Yes? What if delta x and delta y is not the same? Very good point. If delta x and delta y is not the same, is that going to alter the sparsity pattern of this matrix? No, it's just going to change the values. So I would have a longer expression, but it involves exactly the same 5 terms. It's just the coefficient before the 5 terms are going to be more complex. That's it. All right. Yeah. Xing? If the diagonal is not full rank, one of the ways that converts it into a matrix you can solve using Jacobi iteration is called a permutation. So you can change, you can switch the rows, you can switch the columns, and basically, if you know some elements has a large value, non-zero, you can basically through the permutation, changing rows, changing columns, put the big entries on the diagonal. I mean that works most of the time, but like there is no guarantee it'll work. Yes. What is the convergence criteria of U? Very good point. So I'm going to talk about the error analysis later. The convergence criteria is usually based on what's called the residual. The residual is RK is defined as B minus A times UK, right? That is something you can compute every iteration if you want. And if the RK is 0, you know I have exactly the solution. If RK is very small, well, you need to know what is the, again, what is the norm of the inverse of A in order to know how big your solution area is. So if you want a certain solution area and you have a rough idea of what is the norm of the inverse of A, or sometimes the condition number of A, if you remember in linear algebra, then you have an idea of how small of a residue you need to obtain for you to stop the iteration. Good point. Okay, any other questions?